Okay, our next speaker of this session is Zhixuan, and he's going to tell us about modular models of monoids with operations. Yeah, please take it away.
Okay, thank you. Is it working? Okay, cool. Hello, Internet. Hello, everyone. Welcome to my talk. This is my talk, Modular Models of Monoids with Operations. I'm Zhixuan. This is my joint work with my supervisor, Nicolas, who's going to be here tomorrow. And this talk is about mathematical models or computational effects in programming languages. And the goal of this talk is going to develop a new perspective on algebraic effects, which encompasses more general forms of operations, such as exception catching, parallel composition of concurrent programs, and acquiring a log, and so on. And this new perspective also encompasses computational effects that are not monads, but are, for example, obliquity factors, gradient monads, and so on. But before I explain what all these things mean, I will spend the first half of my talk on a brief recap on the history of modeling computational effects. So if all this stuff don't make sense to you now, hopefully they will make more sense in 10 minutes. 35 years ago, Eugenia Moji pioneered using monads, a concept from category theory, to give semantics to non-pure features in programming languages. This is the starting point for us today. But let's first review what a monad is. Some of you may instinctively tell us a monad is a monoid in the modular category of end functors with conversation. That's exactly right. But today, I'm going to do it in a slightly different way. We are going to use internal languages of categories to present category theory as much as possible, since I figured most of my audience here are more familiar with type theory rather than category theory. The internal language of categories is what may be called Eulery type theory. Eugenia Moji originally called them monadic multi-sorted algebra theory, but obviously I prefer the name Eulery type theory. A Eulery type theory has three things. It has a set of base types, O, and a family of sets of primitive terms, H, and a set of judgmental equalities, E. This type theory is extremely simple. It has only three rules. The only type formula is just using a base type. And the only two term formulas are either using a variable from the context or using a primitive term from the set H. And E is a set of judgmental equalities between terms of this language. For a simple example, let's consider a cute little category with just one object star and two morphisms, the identity morphism and another morphism called F, where the composition of F and F is the identity. Then this little category is presented by the Eulery type theory with just one base object, base type, and one primitive term F, and one function saying that f of x is equal to x. So these three rules are the only rules we have for the Eulery type theory in general. But for some Eulery type theories, we may have some additional structures, such as function types or product types. And in this type theoretic setting, a monad is just a type constructor, where the intuition is that for every type tau, the type t tau is going to be the type of computations that computes tau values. And the type constructor always comes with two term formulas, the return and the let in on the slide. Which says for every term E, the term return E is supposed to be the computation, the pure computation that just returns the term E. And the third rule says whenever we have a computation E1, which computes some tau1 value, and another computation in the context of a tau1 value, then we can have a sequential composition of both of them, which is written as a let in on the slide. And these two term formulas, return and let, are required to satisfy some judgmental equalities. For some well-known examples, we have the effect on mutable state, which is modeled by the monad, the state monad, S arrow tau cross S. But of course, this monad only makes sense when we have the arrow type, the function type, and the product type in the Euler type theory. And the effect of exception is modeled by the maybe monad, tau plus 1, and non-determinism is modeled by the least monad. These are just the simplest examples of monads, but we have more sophisticated ones modeling, for example, high-order store or concurrency, etc. One question is, where do these monads come from? Right. We shouldn't expect ourselves to just be able to spell out a monad magically whenever we have a new computational effect, right? They should logically come from somewhere. One answer given by Gordon Plotkin and John Powell is that we should understand these monads by thinking about the algebraic series of the effectful operations. And algebraic theory is just a bunch of operations with a bunch of equations. You may know the algebraic theory of monoids, which has two operations, a barrier operation and a Modularly operation, and the equation says that the barrier operation is associative and so on. So here the perspective is that we should understand monads by thinking about the algebraic series of their operations. For example, the theory of non-determinism has two operations, and or, which is supposed to be the non-deterministic choice, and the Modular operation fill, which is supposed to be a failure. The equations kind of depend on what we mean by non-determinism, but usually we have at least associativity for choice. Another well-known example is the theory of state, where the operations are get and put for reading and writing the state correspondingly. And the equations characterize the interaction between reading and getting. Here I'm just going to show one of them, saying that one put directly followed by another put overrides the first one. Algebraic theories are eventually for talking about models. A model of an algebraic theory is basically a type equipped with terms that implement the operations on this type. For example, a model of the theory of a state has three things, a type A and two terms P and G, which implement the put and the get on this type A, and they are required to satisfy the equations of the theory of a state. And moreover, when the underlying Euler type theory satisfies certain conditions, which I'm gonna sweep in under the rock for this talk, every algebraic theory has three models, which are intuitively just syntactic terms of the operations from the theory and quotiented by the equations from the theory. For example, the free model of the theory of a state over some type tau is this quotient inductive type here, where the mu x is a bounded for recursion, and tau means drawing a variable from the type tau, and s cross means a syntactic put operation, and s arrow is a syntactic get operation, and we then quotient this data type with the equations from the theory of a state. And it turns out the resulting type is just isomorphic to the state monad. And indeed, many monads that we use to model computational effects can be obtained in this way from their algebraic series of operations. So Plotkin and Powell's paper was titled Computational Effects Determine Monads. And since free models are basically syntactic terms, so whenever we have another model A and a function, and a term R that maps the variables tau to the model A, then we have a fold of the syntax trees, which I'm writing as a handle width on the slide, because the operational intuition is that every element C of the free model is a computation that invokes the operations from the theory, and the semantic model A here provides the implementation. So they handle the operations just like a system kernel handles the system calls from the client program. And this construction was turned into a language feature now known as effect handlers by Brokin and Mattia Predner. And effect handlers turns out to be a very useful language feature. So it not only allows the programmer to easily define elements of the free model and handle them with semantic models, they have some very nice properties making them very suitable for many practical purposes. The first thing is what I'm calling syntactic modularity here, which says the algebra series of two effects can be easily combined by taking the co-product of their operations and the co-product of their equations, and maybe also adding some new equations characterizing their interaction. And another thing is what I'm calling semantic modularity, which means effects can be modularly handled. So if a program invokes operations from both sigma 1 and sigma 2, then we can first handle sigma 1 operations and even sigma 2 unhandled. Yeah, so far I've just finished with my mini lecture on the history of modeling computational effects. But what's new in our paper? The new things in our paper are motivated by two issues in algebraic effects. The first thing is that we noticed that sequential composition isn't a real operation in the algebraic theory of an effect, but instead it is an emergent operation that happens to exist on the free models. So consequently, we cannot use equations to characterize the intended behavior or intended interaction between operations and sequential composition. So for example, in non-determinism, we may want to state the property that every computation x followed by a failure is equal to a failure. But here, x stands for a computation, an element of a model. But in general, a model doesn't have a structure for sequential composition. So we cannot meaningfully state this property as an equation in algebraic effects. And moreover, sequential composition on the free models necessarily satisfy a property sometimes called algebraicity, which says that sequential composition commutes with every operation. But in practice, many operations just don't satisfy this property. So we cannot use algebraic effects to model these operations. And some of you may know there are some concepts that we also use to model computational effects, but they are not monads. But algebraic effects are only about monads. So that's one more limitation. So these issues motivate our work. So first of all, to make sequential composition a real operation in an algebra theory, we shift our perspective from algebra series of operations on types to algebra series on monads with operations. And we also generalize from monads to the more general concept of monoids in monoidal categories. So we can model things like a series of operations on objective functors. And of course, when doing so, we'd like to preserve the nice properties of algebraic effects, the semantic and syntactic modularities that I just mentioned. But let me first recap what a monoidal category is in our type theoretic setting. Compared to Euler type theory, the internal language of monoidal categories has a new type former, the box here, which is a linear product type. It has a term former, which is the first rule here, allows us to pair together two terms. And notice that also this term former, this rule here, introduces contexts with more than one variables into the language, which we previously didn't have. And the context in this language is linear, so we cannot throw away or duplicate variables. And in fact, it is very linear. We cannot even exchange the order of variables in the context. And we also have an elimination rule here, which I'm writing as the match here, which allows us to unpack a monoidal product into two variables into the context. And in fact, there's also a similar monoidal union type I, which is quite similar, except that it has 0 components instead of 2 components. The two rules, the two elimination rules and introduction rules are required to satisfy some usual beta eta judgmental equalities. And using this type theory, then we can express the theory of monoids in the way that exactly basically you are expecting. So the theory among of monoids has 2 operations on some type tau, a mu and an eta, and eta is the left and the right identity of mu, and mu is associative. So syntactically, this theory looks exactly the same as the usual algebra theory of monoids that you may expect. But the new thing is that this type theory can be interpreted in any monoidal category. So for example, if we interpret this type theory in the category of endel functors, where the monoidal product is interpreted as sequential functor composition, then monoids become monads. And instead, if the monoidal product is interpreted as something known as the day tensor product, then monoids become obnegative functors. So monoids in monoidal categories are a very general construction that encompasses many abstractions that we use for modeling computational effects. But what we are really interested in are monoids equipped with operations. The theory of monoids with operations is just the theory among monoids equipped with a new operation, up, whose signature can be an arbitrary functor, which is very general, and it may have some new equations characterizing the properties of this operation and even maybe its interaction with the monoid structure. And in this setting, we can easily recover the old things that we have. For example, the theory of throw can now be a theory of monoids with operation whose signature is the constant functor to the union type, and the theory of the state has a signature functor which is the co-product of a put operation and a get operation, and it has equations including the algebraicity, which says a put and get commute with sequential composition, and also the other equations characterizing the interaction between put and get. So all things can be recovered. What are the new things? The first new things is that now we can model more general forms of operations. In particular, we can model operations which do not satisfy algebraicity. And the operations include exception catching and parallel composition. Now they can be modeled. And secondly, now we can mention sequential composition meaningfully in equations. So we can now set the equations that we couldn't do before. And since we have generalized from monads to monoids, now we can talk about theories on obnegative functors and gradient monads and so on. And just like what we had before, every such theory has free algebras, and in particular initial algebras. And since such a theory extends the theory of monoids, this initial algebra, of course, has a structure for monoids. So we have just generalized the principle of computational effects determining monads to computational effects determining monoids, and in a slightly more general way. And this initial algebra is just something like a tree structure quotiented by the equations. So if we don't have any equations, and we specialize the monoidal product to functor composition, then this type can be readily implemented in Haskell as this type, which is quite similar to the usual free monad in Haskell, except that now the signature functor can be a higher order functor rather than an ordinary functor. My co-author Nick is going to have a talk in the Haskell Symposium going into more details of this data type. So if you are interested in the actual implementation of the things that I've been talking about, don't miss his talk. And there are also, thank you, and there are also a few theoretically interesting things that we can say. First of all, we can organize all the series of monoids with operations into some subcategories, which I call series families. So first of all, we have the series family of algebraic operations, which includes all the series of operations whose signature has the shape A box tau. And we have the series family of scoped operations, which includes all the operations that delimits some scopes, just like exception catching. And we have the series family for variable binding operations, which includes operations like lambda abstraction. And it turns out the series family of algebraic operations play an interesting role. So first of all, we can show that the series family of algebraic operations has a category. It is equivalent to the category of monoids in the Euler type theory or monoidal category. So we have generalized the classical monad theory correspondence to an abstract monoid theory correspondence. And moreover, we can show that the series family of algebraic operations is a co-reflective subcategory of a very wide class of series. And the co-reflector preserves initial algebra, which practically means that as far as only the syntax is concerned, more complex forms of operations can be simulated by algebraic operations. Yeah. The next thing I'd like to say is that semantic modularity in the full generality of our framework is not automatic. So this is different from traditional algebraic effects. So instead, we need to recover semantic modularity by formulating a notion of modular models. A modular model M of some series gamma among a series family F is basically a collection of mappings which maps a monoid equipped with some sigma operations, where sigma is in the family F, to a new monoid equipped with both a sigma operation and a gamma operation. So modular models are pretty much like monad transformers. Monad transformers sends a monad to a new monad, while my modular models sends a monoid equipped with operations to a new monoid equipped with more operations. And of course, we show some ways to construct such modular models in our paper, which you may go into if you are interested in. Yeah, that's basically the things I want to talk about today. So the take-home message of our work and my talk is that it is beneficial to do a shift of perspective when considering algebraic effects from considering algebra series on objects or types to algebra series on monads, or more generally, monoids. And this shift of perspective gives us a lot more generality. Yeah, thank you.
Hello, this is Zhixuan from Yale. A very nice talk. You said you can support parallel composition, right?
Yep.
Do you consider concurrent objects, or do you even try?
The meaning of parallel composition can vary a lot. And what I mean here is that we can consider a particular theory of concurrent composition. And the version that I consider is pretty much like pi calculus.
Okay. But the modularity you defined in the previous slide seems to say you can, I assume sigma and gamma can contain different operations, right? So could parallel composition and sequential composition be part of sigma?
Yes. So sigma here, so here, for example, gamma here can be in particular the theory of parallel composition, and a modular model, which we do have one for this theory, for the theory of parallel composition, then sends every monad, for example, equipped with some operation to a new monad equipped with parallel composition and the old operations. And this construction is basically quite similar to the existing free models of pi calculus. But I can imagine some other modular models. For example, we may consider some particular scheduling policy, scheduling behavior of this model, of this theory.
Okay, thank you.
Thank you.
Yeah, we have time to take more questions.
This seems to be giving us a very nice general framework for reasoning about the semantics of sort of generalized notion of effects. Have you thought about how to materialize this as a programming language construct?
Yeah, sure. So first of all these things, all these category theory can be readily implemented in some programming languages as a library. And Nick is going to talk about this in Haskell, where we don't have equations, but we can imagine in, say, cubical arcta, then we can program this basically in a very flexible way. But of course, we can also internalize all the constructions as some language features. The design space for this is kind of huge. We can say specialize the general framework to some, say, monads or objective functors, or we can try to retain the full generality of monoids. But that of course means that in this programming language, we need to be very expressive to express monoidal categories and monoids. So likely that language will be a dependent type language where we can express all this categorical concept.
Thank you.
Thank you.
Any more questions from the audience?
I know I have been very abstract in this talk, so if you want to talk to me, chat with me, please come to me.
I will add one question.
Please.
So, you know, we have this original definition of effect handlers, by Plotkin and Power, and also I think we have many variants of effect handlers, higher order effects or latent effects. I'm not sure if you are aware of that. So is that right that I can consider this work as a generalization of some of the frameworks that, okay, and you provide some theoretical foundations to those frameworks?
Yeah, exactly. So one motivation for doing this work is that we are having two variations of algebraic effects. Includes the scoped operations, which my supervisor contributed to, and we have something like the hefty algebra and the latency effects. We are currently having too many variations. So one motivation for our work is to have a just very general framework that encompasses all these frameworks.
That sounds really cool. Okay, let's thank Zhixuan again for this great talk.
Thank you.